Okay, so in the last lecture, I showed you the basic primitives that we can use to build concurrent programs with, things like spawn, send, receive, and so on. But I didn't show you how they could be used. So what I'm going to do in this lecture is build some abstractions that turn out to be useful for building concurrent programs with. Okay. Before I do that, I'm going to return to sequential programming and remind you of some simple higher-order functions, or rather, a simple higher-order function. Erlang does not have a for loop. But we can easily make one. Making one is a higher-order function. Higher-order functions are functions that either return functions or they have functions as their arguments. This is a higher-order function that becomes a for loop, and it consists of two clauses. For max max f returns the list f of max. For of I max f returns the list f of I. That's the head of the list, and the tail of the list is for of I plus 1 max f. So it's a very simple function, and it's called as in the example on the slide. If we say for of 1, 5, fun of I is I times I, and it returns the list 1, 4, 9, 16, 25. That's pretty much like a for loop that you would find in any conventional programming language. But that's a sequential abstraction. What we can do is we can build concurrent abstractions. So the first one I'm going to do is build a remote procedure call. Now this is one way that we can build a remote procedure call. There are actually several ways we can do that, and they take care of different error cases. While I'll show you a simple one here, in a later lecture, Francesco will show you the sort of one we use inside the OTP system, which takes care of certain error cases that this one doesn't take care of. So what is a remote procedure call? A remote procedure call is something that you can use on a local computer. It will make a local function call look like a remote function call. What does it consist of? It consists of sending a message to a remote computer and then waiting for a reply to come back from that computer. So constructing a remote procedure call is pretty easy. It takes two arguments, a PID and a request. PID conventionally stands for process identifier. It's the name of the process that's going to handle the request. We send a message to that, and that message has to contain our own identity. If it doesn't contain our own identity, the remote computer won't know who to send the message back to, and that's supplied by this parameter called self. And then we generate a unique tag. Unique tags done with this line of code, Erlang make ref. And the purpose of that is to pattern match on it when the message comes back. We don't want to send a request to a computer and then get some other message and to not associate the correct response with the correct message. And then we wait for a message here that has tag as its first argument, and then we return response. That's pretty simple. What could go wrong? Well, we don't want to wait forever. So the next thing we could do is we could add a timeout to that. So we could say same code as before, and we just added after time. And if the time that's shown in the slide has elapsed, then we will execute some different code. We can play tricks with this remote procedure call. One thing we can do is we can split it into two. The remote procedure call actually consists of two parts. It consists of a part which sends a message to a remote process, and it consists of a part which receives a message. Okay, so this code has split it into two. Instead of writing our RPC as one function, we've written it as two functions. We said RPC of PID request is tag is Erlang make ref. We send the message and we return tag. And in the second clause, we say wait response argument tag, and that waits for a message whose value is a tuple with two arguments, the first argument being tag. Okay, that might look unfamiliar to you, but if we rename it like that, we can rename the first part as promise and the second part is yield. So we've invented a construction which is called futures. Okay. Futures are things which are hardwired into several programming languages. They consist of a promise and yield step, and you can use them to write concurrent programs. In Erlang, they're not built into the language. They can just be easily thrown together in 2 to 3 lines of code. So this adheres to our general principles. We do not provide built-in mechanisms. We provide primitives with which mechanisms can be built. And so in this example, we have constructed futures from the primitives. The primitives involved here are make ref, sending a message, and receiving a message. Right. So how would you use that? Something like that. You'd say tag is a promise. You give it some function. It's going to compute. You do some computation. When that computation is over, you can say value is yield of tag. But our promises and futures, are they nice abstractions to program with? Well, some people think they are, others don't. Some other languages have a par-do, par-end construction, parallel do. So in languages like Occam, you'll find a par-begin, par-end, and a sequence of statements. And this construct in a language means do these statements F1, F2, and F3 in parallel. Can we make such an abstraction in Erlang? Well, yes, the answer is rather easy. Let's do it like this. We can define this as PMap. It's actually a parallel version of a mapping function. And it consists of 3 lines of code, the PMap. Well, it dispatches the parallel computations in 3 lines of code, or actually in 2 lines of code. S is self. This is the identity of the process that's going to receive the answers. PIDs is this function do of SF, where that's mapped over the arguments of a list. And then we go into a receive statement with the arguments that come from the list of PIDs. This involves several things. It involves a couple of list comprehensions. It involves a spawn and a send and a receive. But having done that, we've made an abstraction which allows us to easily describe parallel computations. So if we were to go back to Simon's lecture, Simon wrote a simple sequential evaluator. If we wanted to turn it into a parallel evaluator, we would have to use this PMap function. So in Simon's case, he wrote an evaluator. If you wanted to multiply x by y, you compute x, you then compute y, you compute eval of x, eval of y, and then you multiply the results together. We could compute x and y in parallel, and having got the results, multiply them together. And that's what this line of code does. Okay, so that was the end of this lecture. And in the next lecture, we're going to talk about handling errors. And as always, the slides and the accompanying material for this can be found on our website.